For COS 226, Introduction to Data Structures and Algorithms at the University of Maine, my term project was an implementation of a B+ tree and a visualization of it. This implementation works primarily in memory. There are probably, there are better in-memory data structures for these sort of things. Usually these B+ tree would be used in something like a database where the data would be stored on disk, but for this illustration purposes, this just runs entirely in memory. My B+ tree, I had it implement the entire, I think pretty much the entire, there might be one or two functions, but the entire map interface. So it can be used anywhere a map can be used, but then there's also some extra functionality that is made possible because of the B tree. The way that it works is there are leaf nodes and there are inner nodes. So this starts out as a leaf node, and as more things are added, see, it gets filled up and it splits. There is a maximum size for the node and a minimum size of the node. If it goes beyond the maximum size, it can split. If it goes below the maximum size, it can either redistribute values between nodes or merge the nodes. So as you've seen, these are splitting, and the keys in the parent node are updating the parent node splits, and there's new root node. One thing about B+ trees is they grow up, so every leaf node is at the same depth down. So you start at the root, and it takes the same number of steps to get pretty much anywhere. The way that this works is everything that I have to try to remember. Let me just look here. Okay. So, okay. Everything less than the key. Okay, see the key here. Everything less than the key goes on the left side, of this label. So here's the label. Everything that's less than that, like alphabetically in this case, because we're using integer keys. The keys can be anything that's comparable, but these are these are string keys. I meant. So these are string keys. So alphabetically, anything less than this label would be, to the left of it. Anything less than this label would be to the left of that. I have sort of these infinite labels as, representing anything that's greater than or equal to, the last thing in the list here. So you get stuff can be added, stuff can be removed. And they could have any size leaf nodes and inner nodes. So the basic operations for how it works is, when you insert a value, it can cause a split. This is showing the leaf nodes here, and I have like a little footnote, little note thing talking about the inner nodes because I didn't have enough room. On this poster, kind of ran out of room, but it kind of shows how it works. So here's the leaf node, which is these ones in the inside. Here, let's say this is the starting configuration. Let's say we inserted a new key, and so this is showing him in the leaf node. So this is going to be like here's the leaf node, here's the inner nodes. But the basic idea, is applied to the rest of it. But anyhow, so we insert key into this leaf node. This leaf node is now too large because it had a maximum of 5 items, and we see now that 6. So what happens is it moves half of this leaf node that was too large into a new node. After that, it updates the links between these nodes, because these leaf nodes are like a doubly linked list, which allows for easy range-based searches. So you could find, for example, I could find everything that's from B to F and get key to A, B, C, D. Maybe there's nothing there. Let's try X. Okay, see, you get the range of values. Actually, I'm gonna first load the other example. This is periodic table of elements. You could search for the element and get the element number. Okay. So, for example, in this case, we got everything that's in the B's. It's inclusive on both sides. So these are like a doubly linked list between these leaf nodes. Okay, so it was inserted and a split. We update the links between the nodes. So now it's like this. But this node, see, this new node has to be where this node is. So this node gets moved by inserting this new label here that could hold them. So we see how it's like this. Now there's this new label here. But now this label has to be updated to point to this node. So this is the basic result after doing a leaf split. This is the new configuration after we inserted G. For deleting, they could be either a redistribution of values in the nodes or a merging. So this is leaf redistribution. It's going to be shown here. So this is the starting configuration. We removed G. So here, G is removed. Now this is too small. So basically what it's going to do is it's going to take some of the values from the neighboring node, is H and I, and it's going to bring them over here, so that both these nodes are now appropriately sized. Neither too small or too big. It's going to then update this parent node, because the H is no longer in the right side, now it's J on the right side. So this is the result after doing a leaf redistribution. With a merge is done if keys cannot be redistributed, because an attempt to redistribute might result in, either one node or the other being too small. So for example, this leaf merge, remove G. So now this is too small. If it tries to redistribute, then this one would have been too small. You can't have it just shift things around. So it's going to merge by copying these over into this node. It's going to remove this node by updating the links to bypass it, and then this could be deleted, and the parent labels can be updated, shifting them over. So, for example, this label, gets moved over to here. And now, this label is no longer correct, because see, before it had an H in here, which is, the greater than or equal to, but there's no H's over here anymore, because now it's, it's been moved over here. So this has to be updated with this label. And the basic idea, this sort of basic idea happens, even with the inner nodes. There's some differences. Let's see. You need to deal with. I mean, I used sort of explicit infinite keys, which everything is like less than. So this had to be updated. Make sure things go where they need to be. But basically, these sort of operations just keep going up, propagating up, until they no longer can happen. So, for example, let's say after a leaf merge, well, maybe the parent key might be too small, so then this has to be either redistributed or merged with one of the other things and going up. And if the root node is too small, then for example, let's say these two here, they merged into one, which means that this only has one child. So then the merged key, would become the new root. So this root is no longer needed because it's too small, and so that root gets, removed. So that's the basic idea of how the B plus tree works. There are different things you could do. You could get, you could query for values. You could check if it contains a value or a key. Like I said, you could do range-based stuff. You can get like everything from the first thing up to the key, so that's everything that's like less than or equal to the key you're searching for. Get key last, which is everything that is greater than or equal to the key being searched for. You could get the range. You could, modify things by added keys, changing values. You could check the size. This is 133 elements. There's 23 nodes. Here are all the values. Here's a set of all the keys. And there's loading and saving functionality for basic demonstration purposes. It's just a text file. It's not the best file format, but it's just for this illustration, for this demo. For the sake of demonstration, I could remove and add random keys, random entries. I mean, key value pairs. Overall, it was pretty challenging to debug, to work out all the problems, debug it. But in the end, it works well. And you can see the visualization of the entire tree here. So, that's the basic. This is my, the basic idea of this B plus tree demonstration visualization program that's written for COS 226. Thanks.